In the late 1800s, George Cantor revolutionized mathematics by introducing the idea of actual infinities in math in terms of different types of infinities as well. This polarized mathematicians to the point where his professional and academic demeanor were completely threatened by other mathematicians and divided mathematics into two main ideas. This became to the point where David Hilbert himself said, "No one shall expel us from the paradise that Cantor has created." And since then, we've adopted these ideas under the axioms of ZF. But what are these ideas and what made them so revolutionary? In order to begin, we need to talk about infinity. Now, you may already have an idea of infinity as potentially you have infinitely many points that are approaching some limit point. You may also think of all the counting numbers as infinite since there's infinitely many counting numbers. But in order to talk about all of these things, we need to first understand what is infinity made out of. And we need to start at functions. Now, a function is a mapping from a set A to a set B. As a reminder, a set is just a collection of objects. Here we have two sets A and B, with their objects corresponding to them. Now, a mapping, which is a function, just takes an object A and maps it to an object in B. Notice how you can have two different objects in A correspond to the same object in B. The only thing is that no object in A can correspond simultaneously to more than one object in B. Now we need to discuss what we mean by saying a function is one-to-one and onto. If this definition looks too complicated for you or you don't understand it, don't worry. I'll break it down into simple terms. Essentially, this definition says that for any two objects A that are different, their corresponding objects in B also should be different. No two different objects in A will have the same object in B corresponded to or mapped by F. Another important idea is the concept of a function being onto. Again, the definition just says something that looks a little complicated, but at its core, it's saying the following. Every single object in B, as you notice every single point, is mapped by some object in A. That means that for any object in B, there is a corresponding input in A. If these two functions, if a function is both one-to-one and onto, we say it is bijective. And this is the core of what we're going to explore now, entering cardinality. Now, you may know the set of natural numbers as 0, 1, 2, 3, 4, or just 1, 2, 3, 4. We'll include 0 for the sake of this video. Essentially, it's just a collection of all counting numbers. Now, again, as we discussed, this set is infinite. But why? This is because the set of natural numbers is an inductive set. That is, if n is a natural number, then the successor of n is a natural number. Just think of the successor as 1 plus that number. Using von Neumann ordinals, it may be thought of as follows, but you don't need to worry about that for this video. This is just a more formal way of putting it. Essentially, there is no finite amount of elements in the natural numbers. There is no largest number because the successor of any natural number is also a natural number. That's what makes it infinitely large. Now, for sets A and B, we say that the cardinality of A is equal to the cardinality of B if and only if we have a function from A to B or from B to A that is both one-to-one and onto, also known as a bijection. Now, you're probably wondering, what does this have to do with infinity? And to that I say, we'll get to that in just a second. The important note is that the cardinality is basically saying how many elements this set has. So this is a precise way of saying when two sets have the same number of elements. Now, in order to understand what this means, I'll give an illustration. Notice how every element of A is uniquely paired with another element of B, such that there are no elements of B left over. That's what it means to be both one-to-one and onto. If this is true, then there's the same number of objects in A as in B, as you can see by this example. This even applies for infinite cases. Our first case example is an interesting one, which is that of the natural numbers and the even numbers. Now, they're both infinite sets, but you may think intuitively the natural numbers should have more numbers. After all, it's 2 times as big as the even numbers. Now, we'll see if this is actually true or not. Now, recalling the definition of the even numbers, we're actually going to prove that there's the same number of even numbers as natural numbers. This means the cardinality of the even numbers is equal to the cardinality of the natural numbers. Now we shall prove this. The proof relies on this idea of pairing. We need to find a function that maps a natural number to an even number such that every single even number is taken account of. Let's try this. Essentially, we're going to take the first natural number and pair it with the first even number, and the second natural number with the second even number, and so on and so forth. If we continue this process infinitely, we will actually perfectly pair each number. The function we're using here is, simply put, f of n is equal to 2n, which takes a natural input and outputs an even number. In order to prove that these two sets have the same cardinality, again we need to show that this function f is both 1-to-1 and onto. So let's start with each part individually. The hypothesis of being 1-to-1 is that you need to have two inputs in the natural numbers in this case, and you need that their outputs corresponding are equal. Now we need to show that n is equal to m. However, this follows straightforward from the fact that f of n is just 2n, and if you divide both sides by 2, you can see that m is indeed equal to n. How do we show the second part? The hypothesis is that we need to start with some number in the output, in the even numbers. In this case, we'll fix a y. And so y should be equal to 2k for some k in the natural numbers. After all, y is even. So can we find an input that actually maps to this output? Is there some number that f of that number is equal to y? Now indeed, f of k is equal to 2k by how we defined f. But 2k we said was y. So we found an input for which the output is equal to y. So every single even number has a corresponding natural number. You can just think of it as dividing the even number by 2, and that gives you the corresponding natural number. Since we showed that there's a bijection from the naturals to the evens, they have the same cardinality, and so they are the same infinity. Although this result may be mind-bending, this may be intuitive to people who believe that there is just one infinity, and it is the infinity. And all infinities are equal. Infinity plus 1, infinity plus 2, infinity times 2. As we will explore, this is not the case, but for these basic sets, it actually is. We consider the integers. As a reminder, the integers consist of all positive and negative natural numbers. Now, can we find a mapping from the natural numbers to the integers, which is both 1-to-1 and onto? In this case, indeed we notice that you can actually map every single natural number uniquely to a corresponding integer, such that every single integer is accounted for. This covers two bases. It is true that every pairing is unique, which is the 1-to-1 aspect, and every integer has a corresponding natural number, which is the onto aspect, and so the natural numbers actually have the same cardinality as the integers. This again may seem pretty intuitive considering our last example with the even numbers, but what about something like the fractions? The rational numbers represent every single fraction of two integers where the denominator is non-zero. Now, what's interesting about the rational numbers is that between any two rational numbers, there exists not just one, but infinitely many rational numbers. So would this therefore have even more numbers than the integers or the natural numbers? Well, the answer is a resounding no. We can consider making a table as follows, starting with choices of p and choices of q. As you see, every single entry in this table represents a rational number. In fact, if we extend this table infinitely, we will cover every single positive rational number. Extend this similarly as we did to the integers to alternating p values between negative and positive, and we will account for every single rational number in its entirety. The question is, can we count these? Well, if we count as I just showed, you actually can. What do I mean? We could start by doing this diagonal method. We start from this entry and move our way down and up and down in diagonal, making sure to count every single rational number. Although this may seem a little weird, essentially what we are doing is that we are able to string together like beads every single rational number, and order them. The fact that it's orderable in this way allows us to count them. And by virtue of it being an injection, right, every single rational number is accounted for. And it is unique, right? You have that the set of rational numbers must be equal to the set of natural numbers in cardinality. If this result seems counterintuitive or you don't get it, I highly encourage you to search it up and try understanding it for yourself. But this is the main intuitive idea of why this is the case and why you can count them. After all, when we say that a set is countably infinite, we're just saying that it has the same cardinality as the natural numbers. Even if it's infinite, it means you can count them, you can list them, and that is the core of the next proof. Question is the real numbers countable? I mean, so far we've been dealing with one infinity, that of the natural numbers, but is the real numbers going to be similar? After all, it only adds irrational numbers to the mix. How bad could it get? Well, the answer is very bad, and we'll show why. Suppose all the reals were countable. That is, the set of real numbers is countable and we can actually list it. Now, for the sake of simplicity, we're going to use binary, but this argument becomes equivalent and even easier with normal base 10. But we're going to assume we can express every single real number in binary and do the following. Let's assume we can list every single real number like this. Now here we're giving a finite example, but in general we can list them infinitely according to this hypothesis. Well, what's the issue? Diagonalization. We're going to take the first digit of the first number, the second digit of the second number, the third digit of the third number, and so on and so forth, to form a new number. Notice how this new number is not included in the list by definition. We specifically chose each digit so that it is not equal to any number on the list. But this is an issue because no matter how we list the real numbers, we can always find another real number that's not on the list. Even if we could include this number, we would still find a new number not included. And so, the real numbers are actually uncountable. We cannot list the real numbers in order, and if we did, we could not possibly exhaust every real number by pairing it with a natural number, as we just showed. This is insane because it shows that even though we've been dealing with one infinity, the infinity of the real numbers is one step up. In fact, we are going to explore the very theorem that made Cantor incredibly famous and polarized mathematicians. This is the actual proof itself that became so problematic even in the philosophy of math. One last thing is that we need to discuss what it means for the cardinality of a set to be less than another set. Now we say that the cardinality of one set is smaller than the cardinality of another set if and only if there is a function that is one-to-one from a to b, but there is no function that is onto from a to b. That means any function you choose could not possibly exhaust every single object in B. Intuitively, we can think of that as saying that there must be more objects in B itself. This leads us to the final, Cantor's theorem. This theorem is revolutionary and incredibly powerful in so many ways. This theorem says that for any set A, the cardinality of A is always strictly less than the cardinality of the power set of A. This is huge because it means that for an infinite set A, we can always construct an even bigger infinity by taking the power set. Now you may be asking, what is a power set? Now if you're not familiar, it is basically a set that its objects are subsets of A. It's a collection of every subset of A. Think of a subset as just selecting some objects in A, either all of them, none of them, or only some of them. However you carve out some objects in A, you get a subset. If we collect every single possible carving, every single possible choice of elements and collect every single possible subset, that gives us the power set. Essentially, the power set of A is the collection of all subsets of A. It is the set containing the subsets of A, and that's what makes it so huge. Now we shall prove Cantor's theorem. The first step is to suppose towards a contradiction that there is a function that is onto b from a. In this case, our b is the power set of a. Now we want to consider a specific set and show that it creates a contradiction. This is known as Cantor's diagonalization argument. In order to understand it better, I will give an illustration. We are going to choose B to be the set of all elements in A who do not belong to their corresponding subset. Remember, F takes us from an element of A to a subset of A. What do I mean? It takes us from a point alpha in A to a collection of points in A. And we're going to let B be that set containing all of those objects who are not in that corresponding subset. As you see, this alpha is outside of the collection it corresponds to. Why do we consider it? Because that introduces a paradox. B itself is a subset of A because we're carving out elements of A, so it's in the power set of A. What is the point? The question that we need to ask? Well, there has to be an element, lowercase b in A, that corresponds to that. That is because we said F was onto. Otherwise, this wouldn't be the case. But is this lowercase b in uppercase B? Well, if B was an element of B, then B would not be in its corresponding subset, which is B itself. If B was not an element of uppercase B, then by the way we define the set, it should be in capital B. But this is an issue. This means that B is in B if and only if B is not in B, which is a contradiction. And so our original assumption that the function was onto is contradicted. Although this is the bulk of the proof, we still need to show one final thing, which is that there is a function that is one-to-one, but this is trivial. What is this function? Well, let's consider the set A. Remember, this function should take us from an element in A, alpha, to a subset of A. Well, what if we just consider this subset to be the set containing A? After all, it carves out a specific subset, and it seems to work pretty nicely. Essentially, this allows us to create a function which uniquely maps every element to a subset. Formally speaking, this says the following. We can define f of alpha to just be the set containing only alpha as its element and nothing else. Now we show it's one-to-one, although this is fairly trivial as well. If we suppose that f of alpha 1 is equal to f of alpha 2 for some alpha 1 and alpha 2, then that means that the set containing alpha 1 is equal to the set containing alpha 2, so alpha 1 itself is equal to alpha 2. This is by the axiom of extensionality, which says that any two sets are equal if their elements are equal. Since these two sets are equal, the elements, which in this case are only A1 and A2, have to be equal. However, this concludes the proof. We've shown both that there is a one-to-one function from A to the power set of A, and that there is no onto function from A to the power set of A. Hence, the cardinality of A is less than the cardinality of the power set of A. Notice we made no assumptions about A besides saying that it is a set. We know that infinite sets in set theory actually do exist. I mean, we've constructed some in this video. And so, since we have sets that are infinite that exist, and their power sets also exist, we have that you can construct a sort of hierarchy of infinities, which creates infinitely many infinities. This was the idea that was so absurd and counterintuitive at the time, and made Cantor become an outcast in the mathematical community. The idea of a hierarchy of infinities, and infinitely many infinities, and different infinities was absurd to behold, and yet it is entirely true, as we've just proved. Now, the question of whether there are infinities within these infinities is actually unsolvable given the axioms we have. But the important part is that these ideas permanently created a mark on 19th and 20th century set theory and actually introduced more debate into the question of the philosophy of mathematics. Now you have both a piece of history and math to take with you and an understanding of what is infinity. So next time your friend asks you, Is 2 times infinity bigger or smaller than infinity? You have the answer. No, but there is an infinity bigger than that infinity.